So let's take a look at a solenoid that I will have hooked to a power supply, and then I will throw a switch into it. So right now there is no current flowing through it because there's not a complete circuit, and you need a complete circuit. Current has to go somewhere. So I make the connection, and suddenly the current goes from 0 to something. So suddenly I have a current flowing through here. Now the current will pick up very quickly, but it does pick up. It's not instantaneously there's a current there. We've done in another video where the magnetic field is equal to mu naught times N times I. If we look at the magnetic flux here, since I have a current flowing through it, creating a magnetic field, this magnetic field is going through the middle of the coils, which means that I have a magnetic flux here. So my magnetic flux is going to be equal to B times A, but recognize that's the area of one coil, times the number of coils. Generally, N comes first, and so let's go ahead and, yeah. So that's the area of one coil, that's the number of coils, and that's the magnetic field. Since my magnetic flux is changing, because my current is changing, I have a change in the magnetic flux over time. That's going to be equal to the change in NBA over time. Now on a solenoid, if you think back to the solenoid, that area is not going to change. You know, I can squeeze it and you're not noticing a lot of deformation, and it could be just that I'm weak, but this area is going to be close enough to constant. So area is constant. The number of coils is constant because I'm not damaging it. So in an A come out front, and I'm left with the change in the magnetic field over the change in time. And that is going to be equal to the negative of the voltage. So let's put the negative sign on the usual side. So it's negative in A change in B over change in time. B, that's the magnetic field there. So as the current builds up, it's going to build up. Let's go ahead, since I have capital in here and lowercase in here, let's go ahead and synchronize those. Remember that this is the coil density. So this is mu naught times the number of coils over the total length. And I want to use lowercase l here, not an uppercase L. Uppercase L I'm saving for something else in just a moment. So where this is the length L. So this becomes negative N A times the change in mu naught N over L times I over change in time. Well, mu sub naught is just the permeability of the space inside there, and so it's going to come out. Number of coils and the length are staying the same. Again, just as I can't squeeze it and deform it, I can't also push it or pull it and deform it. Not easily. And definitely a current's not going to do it. It's not like it's a slinky. And so these are going to come out. And so this becomes negative mu naught N squared A over L times the change in the current over the change in time. This right here is dependent upon the solenoid. Depends upon the area of the solenoid, the number of coils, and the length, overall length of the solenoid, and upon the permeability. This is more of a constant. I could stick something inside it, and that solenoid does come with a rod that we could stick inside of it to make that into a mu instead of mu sub naught. But we're going to stick with mu sub naught for right now. This is known as inductance. And the symbol for inductance is a capital L. So this would have a specific inductance. This would have a different specific inductance. Talk a little bit about inductance here. The units of inductance, SI unit, is the Henry. I mentioned this in another video, but there is an inverse Henry, which is the Internet, or however it's pronounced. And again, legitimate word game word.